What if I told you that brain implants did not start with this?
Elon Musk makes some very cool things. Neuralink.
That person is now sharing how his life has changed since.
Neuralink had been making waves in the media for the last 2 years, with audacious goals to control human brains, and now over 7 patients implanted with one of their devices. But BCIs, or brain-computer interfaces, as this technology is formerly known, is a lot more nuanced than that, and it has surprisingly been around for a really long time. In this episode, I want to go on a journey with you to understand this incredibly complex organ, our brains, and our quest to control it. This story starts over 100 years ago. Don't worry, we will only cover the most interesting things. But undoubtedly, the biggest part of the story has yet to be written. My name is Yoda, and I'm a science and tech journalist. My background is in cancer biology and understanding how cancer cells get into the brain, so I'm a little bit biased. But if you love science and tech explainers, follow along for more. So let's wind the clock back for a minute in 1791, when this guy, Luigi Galvani, understood for the first time how our brains might indeed work with electricity. You see, there were all kinds of very weird theories about how our brains work. Aristotle thought the brain was a type of radiator, balancing heat and keeping only the good type inside. And over the centuries, lots of very weird theories about the brain. But it was only in the last 200 years that we truly start to understand how the unit of the brain works. But this all happened very slowly. It takes over 100 years for this guy, a British physician named Richard Canton, to show that the brain's electrical activity is something that can be measured from the outside. His experiments are on animals, and the guy truly had a lot of other hobbies, so this kind of falls through the cracks, so to speak, until another 50 years pass. This time, a German psychiatrist, Hans Berger, wants to truly understand what is happening with electrical activity in the brain and how is it involved in both health but disease. And he discovers the EEG, the electroencephalogram. Now, you might think that that is not a brain implant. And in a way, you're correct because it's a device that goes on the other side. But I want to show you how there's 2 very important sides to BCIs. One is understanding what is happening to the brain, and not only understanding, but being able to measure it with really high accuracy. And on the other side is being able to control the brain. These first EEGs back in the 1920s were our very first steps in understanding how to read the human brain. And for that, we need a few more decades to pass for the true grandfather of BCIs to come into the scene, Jacques Vidal. Vidal is a researcher at UCLA who is absolutely immersed in this idea of creating a device that can truly control brain matter. In 1973, he coins the term brain-computer interface, and just a few years later, he publishes one of the very first studies on controlling a device using only our brains. In 1977, he uses a very specific type of EEG, known as visual evoked potential, a type of EEG that can read specifically the activity that is happening in the visual cortex when visual information enter our eyes and get understood by our brain. He trains 10 volunteers to be able to control a cursor on a screen just using their eyes, and he exhibits the results by making them guide the cursor through a maze. This is absolutely huge. And it shows the most important thing I want you to take away from this video, which is that our brains are not just a storage mechanism. Just like a computer understands zeros and ones, your brain understands electricity and chemistry. The ability for your neuronal cells to get excited, evoke an electrical potential, and then release chemical agents into synapses, control and store every single thing about you. Every single sound wave that I'm sending your way gets translated into electrical potentials in your auditory cortex right now. The photons from the screen hitting your eyes are getting translated nearly in real time into a perfect visual input, a perfect video that is understood by you. And most importantly, these electrochemical interactions store and understand your personality, your thoughts, and your feelings. But brain implants were not just created to understand our brains, but to solve real problems, because either through genetics or accidents, this vital cord of information in or out of the brain gets cut. People with damage to their retinal cells can no longer decode the photons that are hitting their eyes. People with congenital hearing loss and problems in their inner ear cannot translate those sound waves and vibrations in the inner ear into the auditory cortex to be able to be heard. This is one of the most fascinating aspects of brain-computer interfaces, because one of the most common BCIs has been used in over 1 million people to this day, and that is the cochlear implant. Just 1 year after Vidal's cursor and maze experiments, Professor Graham Clark, just around the corner over here in Melbourne, performed the first cochlear implant, a tiny electrode connected to a microphone that goes inside the inner ear, that deciphers the different sounds and translates them back into those electrical signals that the auditory nerve can carry back to the brain. But you're probably thinking, this is a very specific application for BCIs. What about Neuralink and all these other companies that have been making waves right now, showing implants into parts of the brain that we previously thought were inaccessible, and that perhaps can do a lot more than just one function, but can control muscles, understand feelings, thoughts, speech patterns, and so much more. And to understand this, we need to go back to physiology for a second. You see, while all this incredible science is taking place in the BCI front, our understanding of the human brain over the 20th century absolutely explodes. Part of this is a very important finding that each tiny region of our brain does a very, very specific thing. We used to think that our brain just functions as a giant soup and everything does a little bit of everything, but this was shown to be absolutely wrong. Just to give you a very interesting example of how specific your brain can get, there is a handful of people in the world that have suffered a tiny stroke in one very specific part of their visual cortex, is known as V5. Those tiny groups of cells, their only job is to understand direction and motion, leaving these people with a condition known as akinetopsia, which means that they can perceive the world around them and stationary objects accurately, but when something moves, they cannot see that movement or the direction that it is going at. That is absolutely wild. But let's get back into it. Since Vidal and the first cochlear implants, there's been iteration after iteration of brain-computer interfaces. Deep brain stimulation that is helping Parkinson's patients with movement disorders, and so much more. But what is happening right now? Because it truly feels like we are at this precipice of this new era of BCIs that are unlike anything we have created before.
Yep. So you're right. There's an entire range of neural interfaces, ranging from incredibly uninvasive devices, patches that can sit on the outside of the skin, using different methods. This could be ultrasound, this could be electronic, all the way to devices that sit very, very close to the area that you're focused on, that you're interested in. And we call these implantable or invasive neural interfaces.
This is Ben Boodington, founder and CEO of Coherence Bio. They have designed a type of implant that doesn't just go into the brain, but can assist cancer patients. Because it's not just brain cells that understand electricity. Cancer cells have been found to have completely unique patterns of electrical activity to healthy tissue. But in order to understand brain implants, you have to understand this. Because it's not just about going on or inside the brain or outside the skull. For the longest time, we thought that you needed to be in direct contact with the brain in order to truly be able to control it. But that era ended in 2021. This is a stentrode. It's designed by Synchron, a BCI company that does not require brain surgery. Doctors can implant this device by guiding it through a catheter from your neck into the precise location inside the blood vessels that are inside your brain's motor cortex. In November of 2020, 2 patients with amyotrophic lateral sclerosis, a type of disorder that leaves patients locked inside their own bodies as they cannot control their muscles and perform any motor functions, but they can think and understand everything that's happening around them. Using the stent rod, they were able to control an external device, text, email, communicate, and even order groceries. And this was the first time a BCI was implanted without the need for brain surgery. Just for comparison, this is a totally different approach to Neuralink, because Neuralink is not an implant in itself, but it's more like 64 tiny hair-like structures, each one thinner than a piece of hair, that get implanted using a robot. They're implanted deep into the brain matter. Altogether, they contain over 1,000 electrodes, each one picking signals from one very specific part of the brain, in order to allow patients to control an external device. But BCIs are facing a few very difficult challenges. You see, our brain is still living matter, and when something foreign is implanted into it, it attempts to fix that damage by forming a thick type of scar tissue around it. That can make those electrodes less and less efficient over time. Because of how risky this technology is, it's at the moment only trialed for people that have reached the end of the line with every other type of intervention that we currently have possible. But it's also an extraordinary beacon of hope for the patients who need it the most. There's currently over 250 companies developing a type of BCI. One of the latest ones is Beinow1, a Chinese company that has designed this electrical cortical graft pad, a type of implant that will be placed right here, practically on top of your brain. It was trialed in patients with ALS also earlier this year, and the researchers behind it are trying to tackle another challenge, which is cost. Most implantable devices in the market right now will cost anywhere from $40,000 to over $100,000. Beinow is hoping to develop a product that will be able to be offered for less than $1,000. In other words, BCIs will come in all kinds of shapes and sizes, solving all kinds of different problems. And there's so much hope in restoring quality of life for millions of people around the world using BCIs. At the same time, BCIs are touching on the very essence of our being, and they come with very significant ethical considerations. But next time you see headlines about brain implants, I want you to stop and think a little bit about how they go, who are they for, and what were they made to do? Because all these questions are very important in making sure that this technology doesn't just become this scary, big, weird thing that we don't even want to discuss, but something that we can continue to develop for good. If you watched this far, please subscribe, and thank you so much for watching.